In this video, we're going to look at area estimation with finite sums. Now, there's plenty of shapes that we know how to find their area. For example, squares, rectangles, triangles, circles. All of these shapes we know how to find their areas directly just using formulas. But what if we have some sort of a curve? Well, this curve, not so comfortable with this. We don't have a formula to figure out what is the area underneath of this thing, how much space is in here. So, maybe it's semicircular or kind of has a circular pattern, but it's not a circle, so we can't say it's just a quarter of a circle. It's clearly not. And then what happens too, as these patterns become more and more irregular, that now this has lost all semblance to any sort of shape that we know. And so one of the easiest ways we can do this area estimation is by using a shape that we do know, or at least a lot of that shape that we do know, which are rectangles. It's very easy for me to start drawing rectangles, and for now I'm just going to stick to this green shaded region. I'll ignore that more complex shape. But we can see that if I form some rectangular type regions under this curve, they're not a terrible approximation. Now, they're not dead on, so there's a few ways that I can figure out how to draw these rectangles. One way is to use the higher or the upper bound of each of those rectangles. So I'd be going from the right, kind of drawing it as I'm doing. And we can see that I've overestimated, in this case, by all those red regions, right? It's an overestimation. What I could have also done is I could have used the lower of the endpoints, and so that would be the left-hand endpoint, so that rectangle. And now what we see is we've actually underestimated by that blue region there. So neither of these methods is perfect, but I think we can see it's a decent approximation. Let me try and redraw the same shape. It's supposed to be the same. What we can hopefully see too is that the more rectangles I put in this shape, the more accurate it'll be. So as it was, I had 4. If I only used one rectangle, that would have been very inaccurate. So I would have either gone off, let me use the same colors, I would have gone off the upper, the red, and I can see that I have a much too large approximation there. Or I would have gone off the blue and I would have 0 area. That would be much too small. I could have used 2 rectangles, and that's still not going to work out for me real well because, again, it's just we're trying to apply too big of a region to make one shape fit it. It's not very rectangular. But if I take that shape, and this time instead of just using 4 rectangles, let's say I just start drawing tons and tons and tons of rectangles in here. I don't even know how many I have. I could count them. But we can see that with all those new rectangles, we're getting a lot closer to what the actual area should be. If I start making those boxes, we can see that for the most part, they're doing a pretty good job. In fact, you can barely see in some places the differences. And so as we get further along the curve, then maybe we start to see more of a difference. But it's still a lot better than these really big errors that we had up here. There's just these tiny little errors, and it doesn't matter if we go above or below. You can see there's very, very small errors on each of those rectangles. But then there's a trade-off to that too. Yes, we've just made it more accurate by drawing whatever this is, 10, 15 rectangles, but we're going to have to calculate these. We're going to actually have to find the area for each rectangle. And do I really want to find the area for 15 rectangles when 4 may not have actually been so bad? I don't know yet. We haven't seen what it actually is. And so that's kind of the trade-off on these things is if we're going to use rectangles, we're fitting a imprecise shape to a very precise region. And the more of that shape we have, the more accurate we're going to make our model, but the less accurate, the more work we're going to have to do. So let's look at an example. Let's estimate the area under the curve given by the function y equals x squared between 1 and 3. And we're going to do this several ways. And so 2 ways that we're going to look at are using lower sums and using upper sums. So this is an initial decision we have to make, and this is what we saw the difference between the red, the upper, and the blue, the lower. Neither is precise, but maybe one will be a little bit more accurate. I'm not sure yet. We'll have to see. And then the other thing that we have to consider is how many rectangles we're going to use. And so I'm going to use 2 rectangles and then we'll do 4. Again, would 100 be better? Sure, but I just don't want to do 100 rectangles. So we'll start with 2 rectangles with both the lower and the upper sum, and then we'll move on to 4. So the first thing that I'm going to do though is I'm going to sketch this out. X squared, we know what that looks like. It is this shape right here, and we're looking between 1 and 3. Now, if we're forming 2 rectangles, that means we're splitting it in half. We can pretty easily on our own calculate what that split will be. We know it's going to be 2. But we need to really have a pattern for doing this. And so the first thing that we're going to have to consider is the rectangle's width. And so we know how to find the area of a rectangle, right? Let's do a little bit of background here. An area of a rectangle is length times width. And again, we're calling the width the x-axis, the length will be the y, it doesn't make any difference. But area is length times width. So for each of these rectangles, we have 2 rectangles right now, we need to figure out their width and we need to figure out their height or their length. Now the width is going to be consistent. I didn't mention this, but throughout this video, I'm going to use even width rectangles. If we had some sort of crazy shape that seemed to be holding to one pretty constant pattern, then all of a sudden it changed, if you want to, you can use different width rectangles, but because we have a pretty uniform shape here, and just for the ease of it, I'm going to use even width. So every width is going to be the same amount. So let's start there. The width of the rectangle. Well, to figure out the width of the rectangle, we need to figure out how far we've gone across. What are our 2 x values? And we're going to divide that up into the number of rectangles we want. So I can write that as delta x over the number, which I'll call n. And so for our 2 rectangle example, our delta x would be 3 minus 1, and our number of rectangles is 2. And so we get 2 over 2, which means we have a width of 1. And so that's giving me how I would get to this next point right here, where I had that little slash. I'm counting by 1 each step. So I'm going from 1 clearly to 2, as we already said, and then from 2 I'd get to 3. So our widths are 1. Next thing we need to do is figure out our heights. Well, these are going to take us a little bit more work because the heights are inconsistent. It depends where we're at. And so this is where the lower and upper comes into play. If we're looking at the lower, we don't strictly mean the left versus right, because here we saw the lower endpoint was dictated by the left side. That's not a guarantee. It is whatever side of the rectangle is smaller. And so if I look at my rectangle rather 1 to 2, the smaller side is here at 1. And so this will be my rectangle. From 2 to 3, again, the smaller side is at 2. And so these don't have to be consistent. So for instance, if I had some really irregular shape, and I want to break this up into a few rectangles, let's say I was going to break it up into 3 rectangles, and I'm going to do so evenly. So 1, 2, and then 3. We have 3, and they're supposed to be pretty even. Well, if I'm going to look at this first rectangle, which goes from here to here, the lower would be on the left-hand side. From here to here, the lower is on the left-hand side. But then from the third rectangle, from here to here, the lower is actually on the right-hand side. And so lower endpoints there would be left, left, right. Versus the upper, it would be here, here, and then here again. We'd actually reuse that one value. So it doesn't have to be strictly left or right. When we're saying a lower, we're talking about literally what values are lower. And so we're going to be looking at the 1 and then the 2 in this case. So my height, if I want to figure out the height at 1, I'd need to find the function value at 1. And so our function, the equation that gave us the function x squared, we're going to plug that in. So 1 squared is equal to 1. And then 2 squared would be equal to 4. And so those are our heights. And if we think about how to calculate the area of a rectangle, it's length times width, or base times height. So we know that our length is 1, and then the height is 1 in the first rectangle. So our lower sum with 2 rectangles, our area will be 1 times 1 plus, and then the next one, the width is still 1, but the height on this one is 4. So we'd have 1 times 4. And so 1 times 1 is 1 plus 1 times 4 gives us a total area of 5 square units. But what if we want to do the upper? Well, now for the upper, I'm looking at this point right here and this point right here, because those same two rectangles, same two x distances, but if we look at which points are higher, the right-hand sides are higher on those, so we're going to use those larger values. And so I'm actually going to recycle the f of 2. F of 2 would give me the height of the first rectangle, but to figure out the height of the second rectangle, I'm going to look at f of 3. And so f of 3 would get 3 squared, which is 9. And so for my upper with 2 rectangles, again we'll do 2 rectangles. We will have an area of the width of 1 times the height of 4 plus the width of 1 times the height of 9 for a total of 13. So a pretty big discrepancy, and we predicted that the black rectangles, they were undercounting by this space right here and then this space right here. So I'll show the undercount in green, that space, and then this space. The blue were overcounting by this red space, and so we can see that neither is perfect. It's probably somewhere in the middle, somewhere between 5 and 13, not necessarily dead in the middle either. So let's get a better idea then. Let's use 4 rectangles. I'm going to start the same way. I'm going to start with a picture. I always recommend on these starting with a picture. If you draw out the picture, it's just basic geometry. You should be able to figure out the area once you have that picture. So again, we have the x squared. We only care between the 1 and the 3. I'm only going to draw out that part of my axis. But if I'm going to break it up into 4 rectangles, this time a little bit harder to calculate this in between values. So I'm going to start by calculating the width. Remember, we do that by finding our delta x, or the 3 minus 1, over the number of rectangles, which in this case is 4. So we get 1/2. So that means each step I need to count by half. This value right here would be 1.5 or 3/2. Then we'd get back to that 2, and then we'd have 2.5 or 5/2. And so then for our heights, well, it's going to vary based on the upper and lower. So let's start with our lower. And so the lower between the 1 and the 3/2 is the 1. So we're going to need the f of 1. Between the 3 and the 2, 3/2 and the 2, it's 3/2. So we're going to have to find f of 3/2. Between the 2 and the 5/2, it's the 2. It's consistently going to be these left sides because the lefts are consistently lower. So we're going to have f of 2 and f of 5/2. We have 4 rectangles, so we should have 4 different heights. Well, we already found that f of 1 was 1, f of 2 is 4. If I square the other two values, f of 3/2 would be 9/4, and f of 5/2 would be 25/4. Now, we can go ahead and say 1/2 times 1, 1/2 times 9/4, 1/2 times 4, 1/2 times 25/4. That would work, but there's actually a little bit easier way of doing it. If we notice, if we're multiplying the width every single time and we have multiple heights, we could factor that width out. And so the by far easier way to find these rectangles, especially when we have multiples, is to have width times height 1 plus height 2 plus height 3 plus height 4. As long as you have evenly spaced rectangles, even widths, we can factor the width out, simply add up all those heights first, and then multiply by the width. So we know that the width is 1/2. Our heights, we had 1, 3/2, 4, 9/2. Those should be fourths, not halves. 9. Try that again. When we plug in the 3/2 and 3/2 and square that, we should get 9/4. And then the 5/2 gave us 25/4. So we want to have those y values in there, not the x. And so now I'll add these up. So we'll have 1/2 times 9 plus 25 is 34/4, simplifies to 17/2, and then 1 plus 4 is 5. Could of course do this in the calculator. I just don't have one thing in front of me, so I'm not going to use it. When we add those together, we get 27 halves, and then multiplying them, we get 27 fourths. And so that would be our area using the 4 rectangles. If we just think about what that is, approximate it, it's not really an approximation, it's an exact. If we're to write in terms of a decimal, that would be the same as 6.75. So in between the 5 and the 13. Let's do the 4 rectangles, but for the upper. So my width is still 1/2. This time I'm going to need to find some new heights. I get to reuse the 3 halves because the 3 halves would give me the higher of the points. I get to reuse the 2. I get to reuse the 5 halves. And I get to, I need one more. So this time I'm going to get to use the 3. And so I'm going to reuse these 3. The middle 3 are always going to be the same for both. It says 2 ends. Which of the 2 ends are you choosing? And so this time I'm going to start with the 9 halves. 9 fourths did it again, 9 fourths plus 4 plus 25 fourths plus the 9. And so when we add these up, we'll have 13 wholes and 34 fourths, again 17 halves. And so we have 13 is 26 halves, would give us 43 halves. And then half of that would be 43 over 4. And when we simplify that, or when we write it as a decimal, it is simplified. When we write it as a decimal, 11.75. And so if we see the 11.75, again, that is inside the 5 to 13. So if we think about how much each of these moved, the lower moved by 1.75 units, the upper only moved by 1.25 units. So there's still quite a large range there. So I would argue in this case that 2 4 rectangle is not good enough. We're going to need more to really get a better idea, or another process that we'll see in a little bit. But seeing that upper one moved less tells us it's probably going to be closer to the 11.75 than it is to the 6.75. When we're getting those errors, there was error on both the green and the red. Remember, the green was the amount of underestimate the lower model provided, the red was the amount of overestimate the upper model provided. But if we look at the amount of error, the greens are actually a little bit better. My drawing's not perfect, but the greens would actually be a little bit bigger than the reds. The red's probably going to be a little bit closer. The upper is going to be a little bit closer than the lowers. And the same thing would be true here. The areas underneath are a little bit larger than those areas on top. And this one I think I did a little bit better job of than the previous one. We can see that these smaller under triangles are actually a little bit bigger than the ones on top. So the upper estimate would be a slightly better estimator. But it seems like if it's somewhere in the middle, why don't we take some sort of average or use some sort of halfway point? And that brings us to our last idea, which is the midpoint rule. We can use the midpoint of the rectangle to estimate the heights. So the width's not going to change, that part's not going to change, the height is going to be different. So the midpoint rule, we use the midpoint of the x-coordinates of each rectangle to find the height. So let's use that same example. We're going to take the y equals x squared, and we're going to do it with 2 rectangles, and then in a minute we'll do it with 4 rectangles. And let's just draw it again. It's always helpful to have that picture. I'm going to concentrate only on the positive side though. So from 1 to 3. And we're breaking this up into 2 rectangles, so I'm going to cut it in half. We know that middle is 2 because we know that the width is still the same with 2 rectangles. The width we always find by taking the delta x, the 3 minus 1 in this case, and dividing it by the number of rectangles. That is always consistent, doesn't matter which of the rules we're using. Unless we don't want to have even width rectangles, then that would change. But the heights are going to change. So if I think about the heights, I'm looking for the midpoint or the halfway point between 1 and 2, and then between 2 and 3. Well, that would be 1.5 or 3.5, 3 halves rather, and then 2.5 or 5 halves. So I'm going to find the height or the function value at 3 halves and then 5 halves, which we've already done these. They were 9/4 and 25/4. And so to find my area of my two rectangles, I'm going to take my width, which was the 1, and then I'm going to multiply that by the 9/4 plus the 25/4. And when I add those, 34/4 simplifies to 17 halves, which is approximately 8.5. And that is pretty well in the middle. If we go back all the way up to that initial estimate, halfway between 5 and 13 would be exactly 9. It's not exactly. It's going to be closer to one side or the other, but we can see that it is somewhere in between those. And then if we look at the 6.75, 11.75, again, not dead in the middle of those, but it's going to be somewhere in the middle of those. 8.5 is somewhere between them. Now, if we do it with 4 rectangles, our width, same as we said before. Let me start with my picture. So our width is still going to be 3 minus 1 over 4, because we're doing 4 rectangles, which is a width of 1/2. That means we'd have the initial positions of the endpoints of the rectangles of the 3 halves. Scroll up. 3 halves, 2, and then 5 halves. But then I have to figure out the midpoint for each of those. So what is that value in between the 1 and the 3 halves? What is this value between the 3 halves and the 2? Between the 2 and the 5 halves, and then between the 5 halves and the 3. So what are each of those values? Halfway between 1 and 3 halves. Well, if we add those, that would be 5 halves, and cut in half would be 5/4. So we need to be comfortable with our fractions here. 3 halves plus 2 would be 7 halves, cut in half, 7/4. 2 and 5 halves would be 9 halves, and then cut that in half would be 9/4. And then we probably have the pattern figured out. But 5 halves and 3 would be 11 halves, and then cut in half would be 11/4. And so that would be that last position. Just clean that one up there. That is a 9/4. So these are the the 4 x positions at which our heights will occur. So I need to figure out the function value at 5/4, at the 7/4, the 9/4, and the 11/4. And so when we square each of these, they'll all be over 16, but it will have 25 over 16, 49 over 16, 81 over 16, and 121 over 16. And so our area using 4 rectangles, our width is still 1/2. The heights, 20, I'm going to put it all over one common denominator since they all have the same denominator. 25 plus 49 plus 81 plus 121 all over 16. Clean up a couple of those. That was 25 and 121. And so I'm going to quickly add these together. 25, 49, 81, and 121 give me a total of 276 over 16. We still have the 1/2 there. And so 1/2, let me put that 2 there. If we see, can we simplify this at all? 276. We know we can take out a 4, and so we'd have 1/2 times 69 over 16. Sorry, when we divide out the 2, that should be now over 8. Over, one more time, we took out a 4, so we can say that's 69 over 4. And then when we multiply the 1/2 to the 69 over 4, we get 69 over 8. And so if we think about what that would be approximately, 69 over 8 is a whole 8, 0.625. And so we can see that by going from 2 rectangles to 4, we've changed by 0.125. So we're probably pretty close to it at this point. It's not changing by a whole lot. Our margin of error would be probably less than, at this point, a tenth or maybe a couple of tenths, but we're probably pretty close. But is the midpoint always the best? In this case, it definitely looks like it is, but it's not always a guarantee. So we could have some, really irregular shape. Maybe it looks something like this, where that midpoint would be right about here, and that's very much a deviation from what the rest of the shape looked like. So is the left endpoint better there? No, not necessarily. The right? No, not necessarily. Could be if we took some more rectangles, we'd get a better idea. But midpoints don't have to be the best. It's just in a lot of cases, especially when we have a pretty smooth shape or regular shape, a lot of times they might be, but they do not have to be the best approximations. So these are only estimates. We are going to be able to find exact values under curves, but the way that we're going to get to those exact values under curves is going to rely on this sort of estimation. We have been using rectangles. Could we estimate with circles or triangles or rectangles? Sorry, not rectangles, but trapezoids. Any of those other shapes would work, and trapezoids might actually be a better approximation than rectangles. However, rectangles are just the easiest. And what we want to do, if we're really going to have an accurate idea of what this area under this curve looks like, is what we've seen is the more rectangles that we take, the more accurate the estimation. So if we just kept taking smaller and smaller rectangles to where we couldn't even see the space in between them. We knew there is space in between them, but if we just kept taking more and more rectangles, that seems like it's going to be more accurate, and it will be. It's just right now it's a pain to do because we don't have an easy way to write out all those areas. So that's what we're going to look at next. We're going to need to have a way to write out the sum of a lot of things very easily, very quickly. And then we're going to have some way to allow for that idea of taking infinitely many rectangles, because if we could take infinitely many, the closer we get to it, the more accurate our model will be.